Did everybody get a chance to see the list of handouts that you're going to be receiving? Okay, I'll mention these as we go through the presentation. One thing, is Brad in here? Brad? He was? Jeff, where's Jeff? There's Jeff. Hey Jeff, you and Brad might consider getting some of these. This is our presentation. It's called Engine Cooling System Maintenance and Analysis. Today we're talking primarily about oil analysis, and I know we haven't got to it yet, but we're going to. But in conjunction with that, we have a young lady at our office. She's a level 3 on the data analysis team. That's as high as you can get. She's CLS OMA 1 certified, and she's recognized as an industry leader, spokesperson when it comes to coolants. So if you're not familiar with coolants or coolant analysis, this little 74-page book, it should have been entitled Coolants for Dummies, because, I mean, it is awesome. She's written it in layman's terms, and I think this would be a very valuable book for you to get. Get with Jeff or Bill or Brad, and we can get some of these out to you. I don't think there's a cost associated with them. I think we're providing them free of charge right now. So pass that around there. Everybody take a look at it and see what it has to offer. I'm going to change up the routine a little bit. I can't throw these prizes as far as I should when you answer a question. So if you answer a question, I'll tell you to proceed to Bill at the table of gifts and make your selection. All right, let's do contamination control. And you may be sitting there thinking, hey, I thought I was going to learn about oil analysis. Well, we're going to get there. We're going to get there, okay? But we want to understand lubrication. So any questions on lubricant fundamentals? I threw a lot at you. I threw about 40 some odd slides at you. Any thoughts, comments, questions about what you just saw? Did it make sense? Okay. I didn't see any heads nodding, so that was good. That let me know that you were interested in the content. Let's talk a little bit about contamination control. When my girls were little, my wife used to read this nursery rhyme to my girls, and it was called, "This is the house that Jack built." It's a British rhyme. Has anybody ever heard of it? This is the house that Jack built. So our CEO put this to a little phrase to do with, a little poem to do with contamination control. This is the vent plug that breathed in the air, that contaminated the system, that skidded the bearing, that scored the shaft, that shattered the impeller, that shut down the process, that couldn't fill the orders, that lost the customers, that tanked the stock price. Okay? Contamination. The STLE will tell you if you keep contaminants out of your equipment, 80% of your problems will never happen. Okay? I tell people, if you learn nothing else from this class, remember these two things, and I'm speaking towards the maintenance guys now. Filtration, filtration, filtration. Get the dirt out. Desiccant breathers, desiccant breathers, desiccant breathers. Get the water out. You get those two main contaminants out, a lot of your problems never come to fruition. Okay? All right, so let's talk about contamination. My definition of a contaminant is anything in that lubricant that should not be in that lubricant. Okay? We said that you've got a base oil and you've got additives. What if I poured another oil topped off with the wrong oil? What if I had an engine oil and I put an AW32 hydraulic oil to top it off? Is that a contaminant? It's a lubricant. Is it a contaminant? Absolutely. Anything in that oil that should not be in that oil, okay? So the most troublesome factor is contaminants are everywhere. And what are the most common contaminants we're going to see? Air is a contaminant. And I'll explain a little bit why that is the case. We saw that in cavitation and pseudocavitation, that air was a contaminant and caused problems. Water, particulates. What do you think the most common particulate is that we see? Dirt. But it's also some of the wear particles. You know, once those components start to wear, they get in there, they're particulates too. But you're right, dirt is the most common. And then cleanup process chemicals. People ask me about that. What are you talking about there? Well, one of the most common ways that we see cleanup process chemicals get into a lubricant, let's say a guy's got a gearbox and he's got a cap on that reservoir on that gearbox. And you got a guy that's doing maintenance and he's cleaning up his area. And he takes one of these power washers and he goes up and he sees that cap on that gearbox and he sees that there's some dirt and grime around it. What's he going to do with that power washer? He's going to move in on it. And when he does, he's going to drive water into that system, okay? So that's how cleanup and processed chemicals can get in there. Of these top three, which one do you think is the most common that we see and the most destructive? Air, water, or particulates? How many people say air? How many people say water? How many people say particulates? Yeah, particulates. That's the most common one that we see. That's the most destructive. But let's look at each one of them, okay? So let's start with air contamination. What's it going to do? It's going to give you spongy operation of your hydraulics, okay? They're not going to operate like they should. It's also going to cause excessive wear. Air bubbles in an oil are not a lubricant, okay? They're going to reduce the efficiency of that lubricant. Premature oxidation. What did I tell you when you got air with oxygen in it in the presence of a lubricant and you've got that at elevated temperature? What did I tell you is going to happen to that lubricant? You were going to oxidize it, okay? So oxidation happens when you've got air. Pump cavitation, we saw when air gets in through a leaking connection. Increasing layer of foam, perhaps leading to overflow of the reservoir. I don't get too excited when I see foam sitting on top of an oil, because usually the components that are being lubricated is usually submerged in the oil. So I don't get too concerned about it, but if it can be addressed. I had a power plant one time that had their turbine reservoir, and they said, Henry, come look, and they had an oil film on there. So we took a sample of it, went back to the lab, we measured the amount of silicon that was in that sample, and then we knew what the treat level should be based on the size of that reservoir. And I went back with the right amount of treat. We treated that system, the silicon being the antifoam, and that layer of foam went away, okay? So there is treatment for that, but you got to be careful with it. It's like anything. You do too much, you over-treat it, you make the situation worse. So that's why you got to work with a lab on that. But it's more of a cosmetic issue. Where I get excited is when it's entrained or entrapped. You've got these air bubbles within the lubricant itself. And how does that happen? Well, if you've got a low oil level, the air can be whipped into the oil by the gears or pumps. If it cascades into the reservoir, sometimes that will create air bubbles. Insufficient residence time to allow the foam to break. You know, it comes back into the reservoir, and before it has the time to settle and everything break down, it goes right back out. And each time it does that, it becomes more and more entrained, entrapped in that lubricant, because the air bubbles get smaller and smaller and smaller. Air leakage into the pump suction through the pipe fittings, contamination of oil by grease. So a contamination can cause air bubbles. Dirt entering the lube system. Dirt is one of the most common reasons that we see for air in a lubricant. All right, so foaming and lubricating oils. I had a good bulletin on this. I didn't put it on your flash drive, but it was from my old Pennzoil days. And we found that if you had any type of foaming and lubricating oil, it was either one of two things. You had lubricant contamination, which we just mentioned, dirt, grease, something like that, or it was a mechanical problem. It was a design system, something wrong with the design of the system, and so it was creating those air bubbles that foam. All right. Evaluate the pump. So if we've got air in our system, we're going to have to start evaluating things. What's causing that air in the system? So we start with the pump. Well, there is an air leak at the suction side of the pump, which is a very common cause of air entrainment and foaming. A vortex, this little hurricane, will form, and what it will do is that oil level's too low. It'll create that little hurricane, that little vortex, and it'll suck in air. And that's how air can get into your system. Then it goes through the pump, and then at that point, instead of being air sitting on top, it becomes entrained, entrapped in that pump. And each time it circulates, it becomes more and more entrapped. If you've got a pump that's too large, okay, it's oversized for the system, and it's pulling out the oil out of the reservoir faster than it should, it's going to pull in some air as well. Now here we're going to evaluate the reservoir. So that's what could happen with the pump. This is the reservoir now. So if you've got your return line a little too high and it cascades down, you can create air bubbles on top of that surface. That's possible. If you've got a situation here where the outlet is too high or the oil level is too low, this situation right here, you're going to create that little vortex. You're going to suck in air. Up there at the upper right, the inlet is too close to the outlet, so the air bubbles don't have a chance to rise to the surface, so they can't dissipate. And then the other reservoir, the reservoir surface is too small. All the bubbles can't get to the surface. So these are those mechanical issues that we were talking about that can cause air entrapment or air foaming. Solutions for air-related problems. Increase the reservoir temperature. If you warm an oil, typically what will happen is that air will dissipate, remove itself by going to the surface. Now you got to be careful if you're going to warm an oil, because rule of thumb, let's say you've got a hydraulic system here and this oil is going through a pump, it's in the reservoir, you're going to warm it to try to get that air out of it. Rule of thumb is every 18 degrees above 140, you've cut the life of that oil in half. So when you heat it, you've got to be very careful. So let's say a typical hydraulic system is going to run at what temperature, guys, for a hydraulic system? What's temperature, typically? Typically around 120, okay? When you get to 140, realize that every 18 degrees above that, you cut the life of that oil in half. You go another 18 degrees, you cut it now, it's a fourth of what it should have been. So you're reducing the life of that oil. So you've got to be careful when you're warming your oil. Maintain the proper oil level in the pump. Inspect and tighten all joints and fittings. Check proper operations of vents and filters. Filters can cause you issues too. If the filter's too small, it's going to restrict the flow and you're going to start to get air in your system. People ask me, how low can I go in my filters? And I tell people 3 micron. Absolute, 3 micron absolute. I wouldn't go any lower than that. Now I do know there's a universal tractor fluid out there, several of them, that if you go below 6 microns, you can pull additives out of that oil, okay? But my rule of thumb is typically 3 microns. All right, what else can you do to solve air-related problems? Prevent cascading or dropping of the oil onto the surface in the reservoir. Relocate the return line if it's contributing to the problem. And then increase lubricant settling time by installing baffles in the reservoir. So a combination here of mechanical things you can do at the bottom to correct that foaming problem. All right, let's go to water contamination. That's the second biggest problem that we see, and it is also very destructive. Now, this is your oil on the right. This is oil with water. Believe it or not, oil and water do mix if you agitate them together, okay? They will mix together, and that's what you're going to see. So what will happen is, what are some symptoms that you're going to see when that happens if you get water into a system? You're going to see premature failure or excessive wear due to reduced lubricating ability. Just like air bubbles, water is not a lubricant, okay? If it's in that lubricant, it's not a lubricant. Corrosion of bearings or other machine elements, we saw that. Anytime you get that water to the surface, you're going to cause corrosion. You can cause rust as well. Premature filter plugging, and then premature oxidation of the lubricant. Believe it or not, if you get water in there, water's got what in it? Oxygen. Oxygen in the presence of a lubricant, you're going to oxidize it, okay? So those things can happen with water as well. I like this slide because I think it's a very good visual of what can happen when you get oil and water together. Looking at it from top to bottom over here, dissolved water. Water is dissolved in the oil phase. Oil appears bright and clear. I had never heard of dissolved water. I went to work for an oil company. I sold my first load of hydraulic oil. The lab took a sample of it after they blended it, and they came in. They said, "Henry, here's our hydraulic oil, AW68." Back then, we weren't using the Group 2s at that time, but it was just a conventional kind of a straw-colored, amber-colored oil, clear and bright. I said, "Looks good to me." They said, "We just want you to know it's got 500 parts per million of water in it." I thought, well, that's not good. And they said, "You're allowed to have 1,000. I said, "Well, why can't I see it? You know, if it's got water in it, it should be cloudy looking. Why can't I see it?" And they said it's dissolved water, okay? So a lubricant can hold what's called dissolved water, 500 ppm, maybe even as high as 1,000 ppm. And that's acceptable for a hydraulic oil. But after 1,000 ppm, of water in that system, that dissolved water, then you're going to start seeing it. It's going to start to get cloudy once you get above that level. And I'll show you a visual of it here in just a minute. So you do have dissolved water, which was new to me. Then I knew about emulsified water, okay? And so as you get more and more water in that, it changes the appearance. As you first get water in it, it'll be kind of a hazy or a lacy appearance to it. Then you'll see a creamy emulsion, almost like a milk type look to it. And then finally, you'll get so much water in that lubricant that it can't hold it, and it will drop out as free water, okay? I used to sell lubricants to a steel mill up in the Chicago area, and they used what was called a backup roller bearing oil. And this oil had to have good separation from water because these huge backup roll bearings, that sheet of steel would be coming down between them and it would be thinning it out. And as it did, they're spraying water on these bearings to cool them down. Well, inevitably, water would get into that system. They had 2 large reservoirs in the basement. And so they would run on one until they got so much water in it, they would switch over to the other one. And while that one was running, this other one was settling the water. The water was dropping out, and then they would drain it off of that reservoir. And they would just constantly switch back and forth, okay? So, dissolved water, emulsified water, free water.
And Henry, additives can affect that as well.
Yeah. Especially like engine oils. People don't realize this, but the detergent dispersant package in an engine oil wants to emulsify with water. And where I found that out in my career was I had a guy that had a compressor, and they were operating on the Ohio River right next to it, very humid environment. And so the air that he was pulling into that air compressor had a lot of moisture in it. And the manufacturer, the OEM, told them to use a 20-weight engine oil to lubricate that compressor. Well, because of that environment, what happened when that moisture came in? It emulsified. So how did we help him? I said, you need to go get a product that has a good demulsibility. And what did I say was a product that separates water real good? Turbine oil, okay? So you get a turbine oil in there, a 68, TO68, and it took care of the problem. But it was the additive in that oil that actually caused the emulsification to take place. Good point, Bill. Give yourself a gift. All right, the most common sources of water contamination, and there's a whole long list here. You guys probably have more than this. Steam leaks on rotary joints and dryers, leaking pump packing or turbine steam glands, leaking heat exchangers, seals and gaskets. One of the most common things that I see when I'm looking at a customer's data, and I do consulting, we put it into scattergrams and Pareto charts and we look at it. One of the most common comments that I see is seal damage and gasket damage. That's where that dirt and that water and those contaminants are going to get in. Cleanup hoses, we talked about those. The guys moving in with that power sprayer, that power washer. Condensation in storage tanks and equipment reservoirs. We're going to show you what happens with a bulk tank here in just a minute, what condensation can do inside of that. Breathers, atmosphere, the humidity. That's why we say use desiccant breathers. Okay, let's catch that air, catch that moisture, let's catch that dirt before it gets into our lubricant, into our bulk tanks. And then coolant leakage. Coolant's got water in it, so that's a form of water contamination. This is the chart that gives you a visual of what I was talking about when I talked about dissolved water. But we also want you to see not only the change in appearance, but we want you to see what it's going to do to the life of a bearing. So let's say you've got a bearing over here, and here's 100% life, okay? Now you start to get some water in here. And as the water starts to increase, and it increases across the x-axis, 0.05, 0.1, 0.15, 0.2, 0.25. As that water concentration increases, what happens to the life of that bearing? Yeah. It reduces the remaining useful life of that bearing. So you don't want to get that water in there. Now, as it comes down, and we get right here to 0.1%, you've heard me talk in parts per million quite a bit, and I've talked in percents maybe a little. If I wanted to convert this and say how many parts per million of water is that right there, or let's say when they told me, Henry, you've got 500 ppm of dissolved water. That's right here, 0.05. How do you convert that from percent to parts per million? How many places do you move that decimal to the right?
4.
Who said 4? 4 is right. Yeah, so what you do is you move it 4 places to the right. So 0.05% is 500 ppm of water. That 500 ppm of water that they showed me in that sample, it's right here. It's reduced that bearing life to between 30 and 40% remaining useful life, but it's still in that normal appearance. But now, once you get to 0.1, which is how many parts per million? 4 to the right, okay? 1,000 ppm. Now, from that point on, then it starts to look cloudy, then it gets hazy, then it gets milky, okay? That's when it changes over. So, percentages across the bottom, move your decimal place 4 places to the right, and that'll be your ppm. So how much water is too much? Well, for this example, in this table, let's say that you've got, it says here, you've got a moisture level from you got 2,500 ppm. Okay, so this is your moisture level right here, okay? And then the life extension factor is, as you get the water out, you can see across the top how much you've increased the life of this component, okay? So let's say we're at 2,500. The number is 2. We come down here and we reduce it to 156 ppm, okay? So we bring it down to 156 ppm. Down here, coming across, right here. How many times did we increase the life of that oil? From 2 to 5 times, okay? We got life back into that oil by getting the water out of there. One of the most common ways to get water out of a system is something called a vacuum dehydrator. How many guys have ever used a vacuum dehydrator or seen one used? What it does is it pulls that system under a vacuum, it brings that oil in that's got the water in it, and it lowers the boiling temperature. And why does it want to lower the boiling temperature? Because what happens when you increase the temperature of an oil? You run the risk of shortening the life of that oil. If you pull it under a vacuum, like the vacuum dehydrator does, what you do is you lower the boiling point. So you can boil that water off at a much lower level and not harm that oil. So that's how they probably would go from 2,500 to 156 ppm, and in so doing, they've cleaned up that oil. They've increased the life of that system, that lubricant. This is just a visual of what we were talking about, okay? This looks pretty clear. That's 500 ppm. It is a little cloudy, but the one that I saw looked almost like this one right here. The water was dissolved. That's 1,000 ppm. That's 25,000 ppm, and then that's 5,000 ppm. And then across the right there, we've got 10,000 ppm. Just move that decimal place 1 place to the right. So what are some solutions for water contamination? Install a settling tank, much like they did with the backup roll bearings at the steel mill. They had 2 tanks. They would allow one to settle and use the other one in service. Install vapor extractors or wet reservoirs. That's the vacuum dehydrator that I was talking about. Install centrifuge or filter coalescing or on wet systems to remove gross water. So you can have some filters. Sometimes they call them diaper filters that will actually pull the water out. For lower moisture concentrations, install the vacuum dehydrator we talked about. Use water removal filters, which I just mentioned, to remove small amounts of water. Maintain water contamination below the warning level by utilizing oil analysis and offline conditioning. So let's talk a little bit about a tank. You've got a tank, a bulk tank sitting out there, and it's got a couple of open breathers here, and it can breathe in and out. What happens to that oil when it cools down? Does that oil expand or contract? Contract, okay. Then when it warms up during the day, what happens to that oil? Expands, okay. So what is this? This is a breathing bulk tank. And as it breathes, what happens to the area above the oil? What happens? What builds up there? Water, condensation, absolutely. So if I've got this coming in, how am I going to keep this out of my bulk tank? Well, if you install a desiccant breather, what happens is that oil breathes in and out, The moisture is caught in these beads that are in the desiccant breather. And they're very hygroscopic. They want to absorb that water. And when they do, they change color. We have a partnership with Descase. This is a picture of one of theirs. They have blue beads in it. They turn pink as they absorb water. Once they go all pink, you can either buy a new one or you can order a rebuild kit and rebuild it and continue to use it, okay? Now the one thing to keep in mind, when it starts changing colors, it'll either start from the bottom or it'll start from the top. If it starts from the bottom, where do you think the moisture's coming from? Is it coming from the outside or the inside? Inside. That's what you would think. That's what I thought. When I show you a picture of these, they actually flow, the air is reverse. So if you see it pink at the bottom, that means your moisture is coming from the outside. If you see it pink at the top, changing color at the top, that means the moisture is coming from inside, okay? So it kind of goes against logic, but the way that it does it is by the way that the air travels. So the air comes in here and then goes down. So that's what causes the beads to be opposite of what you would expect to see. The other thing about these desiccant breathers is they have a filter media at the bottom and the top. You know, it's not a real strong filter media, but it also is catching some dirt along with the water. So I'm a big fan of these. I'm a big believer in using desiccant breathers. How many guys in here have stationary industrial type equipment where you're using desiccant breathers? Gearboxes, hydraulic systems? Yeah. I'm a big breather in them. Did not know anything about them until I came to work for Polaris. Sold lubricants for 30 years, but learned about the desiccant breathers when I came to Polaris. Okay? All right. All right, let's get to the number one contaminant, the most destructive, and that's dirt. This is a slide, and this came from our DA team, our data analysis team. At Polaris, all of our data analysis team sits in an area at our corporate headquarters in Indianapolis. We've got multiple labs around the world, but all the data comes into these analysts. One of the things they do sometimes is they will take that oil sample and they will create a slide and look on there in a microscope to see what am I seeing here, okay? So what did I tell you they're looking at here? They're looking at what? Dirt. The most common form of dirt is going to show up on our report as alumina silica. When we see silicon go up on the report, when we see aluminum go up, we suspect we got dirt. So this is a picture of dirt. This is what they see under the microscope. Now the analyst was looking at this, and I don't know if you can see it, but right here is a black, kind of a sphere, but it's got sharp, flat edges to it, you know, just broken around the edges. So he's looking at that, and he's trying to figure out what it is so he can put it in his comments. So he can't figure it out, so he calls the customer, and the customer says, yeah, this is from my farm tractor. He said, I got dust in, and I dusted my engine. He said, I know what I did. The guy said, well, it's kind of unusual. He said, I see the dirt, the dust you're talking about, but there's a little black speck in here that I'm trying to figure out what that is. He said, well, that's probably coming from the coal mine next door. There was a surface mine next door, and so that's what that was. So that's why it's important when we get an analysis, when they ship that in, tell us what the application is. We ask, what's the application? Well, he would put agriculture, but by a little bit more investigating on our other guy, we found out that the application, the area, was also surface mining next door, okay? So the environment definitely has an impact when it comes to dirt. All right, so what are some sources of particulate contamination? It can be built in from system components. I actually sold a load of hydraulic oil to a customer. I put in a new bulk tank for him. We had the tank manufactured for him. Shame on us, we didn't flush the tank with solvent before we sent it out. Those welds inside there, that slag, that got in the oil, okay? So they were built-in contaminants from the very start. Generated contaminants from the system. You know, when those particles break off, those surfaces break off, they're going to be contaminants themselves, okay? Introduced during oil sampling. Anytime you open that system up and you pull a sample with a vacuum pump, you've opened it up to outside contaminants, air, water, dirt. How many people in here have pulled oil samples? The majority, okay? How many in here have been trained in the proper method to pull an oil sample? Okay, that's what I usually see. You know, we're gonna get to that here in just a minute. But when you pull that sample, you can introduce dirt at that time. Contaminants from routine maintenance, including addition of new lubricants. Anytime you transfer a lubricant, let's say you move it from the drum to the pail to maybe a pitcher or something and pour it in, every time you transferred that, you opened it up to contaminants. Inadequate reservoir covers and external ingress. Now, it's the most common particulate, causes increased wear. And the best way to stop it, prevent it. Okay, let's keep it out of there. So we're going to do contamination control. We're going to use filters to keep that out of there. We're going to use desiccant breathers to keep that out of there. We're going to do filtration. How many people in here have portable filter carts in your maintenance operation? Good, good. Big believer in those. You know, filtration. When you take that lubricant out of the drum, run it through that filter cart before you put it into that reservoir. Anything you can do to keep that oil clean. This is one of my favorite charts here. This is, do I have an oil pump or dirt pump? We're going to talk a little bit about filters, and I'm going to go into a little bit more detail on filters. I'm by no means a filter expert, but we're going to talk about the size of the filter, the micron rating, and then we're going to talk about, is it a nominal filter or is it an absolute filter? And I'll give you my definitions for those in a minute. All right, let's say E.H. Wolf has just pulled up and is going to drop off a load of bulk oil for you, okay? And it comes in, and its cleanliness code is 211813. Now that may not mean anything to some of you in here, but all you need to realize is the higher the number, the dirtier the oil, okay? So this is not uncommon. This is a very common number to see for a delivery of oil. So let's say that's an AW32, 211813. You bring that in, you offload that off that truck, and you run it through a 25 micron nominal filter before you put it in your tank, as it's going into your tank. So the cleanliness code is going to be 211813. You didn't change that. You're going to run 6,789 pounds of dirt through your pump in 1 year. That's 136 50-pound bags of dirt that are going to go through your pump in 1 year. That's why we say, is it an oil pump or a dirt pump? Now, what happens if we jump in here and say, you know what, I'm going to run that through a 10 micron nominal. I've lowered my micron rating, so I'm going to catch more dirt. That brings it down to a 191613. Now, in a year's time, I'm only going to run 1,809 pounds of dirt through that pump instead of 6,789, or 36 50-pound bags of dirt instead of 136. And because of that, I've doubled the life of that pump because I've cleaned up the oil. Now, let's run a 10 micron absolute, not a nominal, but an absolute. What did I bring it down to? 16, 13, 11. Guys, that is a super clean hydraulic. That is a good hydraulic. 211 pounds of dirt versus 6,789. 4.2 50-pound bags versus 136. I've increased the life of that pump 4.5 times just by going to a 10 micron absolute filter. Do you see what I'm talking about? Filtration, filtration, filtration. I'll let you read this. This is the definition for a nominal rating. This is the definition for an absolute rating. The little dot is my definition, okay? Read the ones with the dash. Those are so mixed up. They're so above everybody's head. Just keep it simple, okay? So, blah, blah, blah. All that means is nominal rating means that it states the percent of a certain size of particle that will be filtered out. So that filter will say, hey, this is a nominal filter, and we're rated at 70%. We're going to catch 70% of these particles at, let's say, 10 micron, okay? We're not going to catch them all. We're going to catch 70%. Now, you take that 10 micron and you say, oh, it's an absolute. Then that states that the size of the particle that a filter will filter out is 99.9% efficient, okay? So when you say, hey, I've got a 10 micron nominal, I'm going to get 60, 70%, whatever the manufacturer tells you. If you've got a 10 micron absolute, you're going to get 99.9%, okay? Here's a question for you. In your car, in your SUV, in your truck, what type of filter do you think the OEMs put into your vehicle? Nominal or absolute? No. Being an engineer, I thought, man, if I build this, I want to take care of it, I'm going to put an absolute filter in it. No. Why do they just put in a nominal? All they care about is what? How far do they want to get? They want to get to that warranty period, you know, and they figure they can do that with a nominal filter. Okay? But that's an excellent question. All right, let's go back here to where we were. Talk a little bit about filtration. This is a filter cart that probably somebody built on their own. And basically, it's not as elaborate as what Brad was talking about. That is, I've seen one of those in service where you've got it on that steel pallet, and when you get it to the ISO cleanliness code you want, it's right there in the letters, in the numbers. So it's powerful. This one here, what you would do is you would say, hey, I built this for about $2,000, and what I'm going to do is I understand that it'll pump about 5 gallons per minute, and let's say I've got a 100-gallon reservoir. It's going to take about 20 minutes. And then I'm going to turn that over 6 to 7 times. And once I've turned that over, based on the filter that I've got on that cart, I believe that I will be at 19, 17, 18, whatever that number is, what you're trying to get to. Okay? That's more of a manual process, just based on, hey, this is the pump rating, this is how much it'll pump, this is how quick we can turn the reservoir over, let's turn it over 6 to 7 times. Now you can get more elaborate with that. Like you can put in a 10 micron and then a 6 micron and then a 3 micron in series, you know, and step down as you filter that. But like the gentleman in the back said, you got to be careful, you know. You don't want to start pulling out additives. So nothing below 3 micron is my rule of thumb, okay? So it's really nice to be able to go around and do hydraulic systems, to do gearboxes. I just can't stress enough. And the stuff that's causing us problems is less than 5 micron. You know, it's in those tolerances where you see 3 to 5 microns. Particles we can't even see with the human eye. You know, we can only see 40 micron or smaller or larger. So filter carts, I love those. Here's an example of where, hey, I've got some product that's been in there for a while. That drum's been sitting there for a couple years. I'm going to go ahead and circulate and filter that product. What do you think the shelf life is on a drum of lubricant today? Anybody want to take a guess?
4 to 5 years.
What was that?
4 to 5 years it's down.
4 to 5. We got a 3 back here. I say 3 to 5. And with the base oil technology we have now and the additives, if that's been sitting for 3 to 5 years, I believe if you laid it on its side and rolled it across this room, everything would go back into suspension. So yeah, 3 to 5 years, absolutely. What about a grease? What's your rule of thumb for the life of a grease? Let's say I've got a keg of grease sitting there. Anybody?
10 years?
Mine is 6 months to a year. Because what happens is, I remember I took the lid off of a grease one time and I got it and I went, oh man, there's oil sitting on top of it. Well, the guy that saw it said, hey, I want to send that back. I went with my tech guy and the tech guy says, no, it's supposed to do that. It's supposed to, that's what a grease does. It bleeds the oil out, okay? So, but usually after a year, I would be concerned about that because it probably would have bled out too much oil, okay? So my rule of thumb is 6 months to a year. All right, so what are we going to filter with this filter cart? Filter the product has been stored for a long time. Product has been stored outside. High oil cleanliness is required if you're trying to bring down that cleanliness of that oil. Filling intermediate oil containers. Anytime you transfer a lubricant from one container to the other, you open it up to the system. You run the risk of contamination, so run it through that filter cart. Okay? Oil drum has been opened without protection from caps or breathers. Okay? They leave the bungs off. You're going to want to filter that. And then oil drum shows damaged or broken seals. Believe it or not, that drum, even if it's sealed, can breathe. It can breathe in dirt. It can breathe in moisture. So you do want to filter those products. Dirt contamination control. Filtration needed on all systems. Cleanliness levels depend on the machine element. I know that when we were looking at that chart, there was a 1297 all the way down with a 3 micron absolute. Believe it or not, I had a steel customer, very dirty, dusty environment, and they were able to filter down to that cleanliness level. But they needed that for their equipment based on what the OEM recommended. Okay, the 3 to 5 micron, that's what's causing us the main problem. And then establish cleanliness standards for each major piece of equipment. You know, is it mission critical? We're going to want to filter that down to a low level. We don't want any dirt, any water, any contaminants getting in there. And then this slide is just showing you all the things that we've kind of talked about. Okay, put some filters in line, put a kidney loop filter on your reservoir. If you're going to move oil out of the reservoir, or if you're going to put oil into the reservoir, run it through that filter cart. Just all those things that you can do to try to keep those contaminants out of your system. Okay, we talked about that. Filtration ratio, I'm just going to show you this. Let's say that I've got 2 filters here, okay? And we're going to run this fluid that's got 200 particles in it that are greater than 3 micron. And I'm going to run it through a B3 filter. This is your beta ratio with a 3 micron filter. 200 particles are going to come, 100 particles are going to come through here, okay? So there's 200 particles that are challenging this filter. There's 100 that come through. 200 divided by 100 is 2. So the beta ratio for this filter is 2. When I look at the 200 particles that challenge this filter, as they come through, we're going to see 1 particle that gets through instead of 100, I'm sorry. 200 divided by 1 is 200. So a beta ratio with a 3 micron filter of 200, beta ratio with a 3 micron filter of 2, which one of those filters is the better filter? Obviously, it's the bottom one, okay? So look at that beta ratio. The higher the number, the more efficient that filter is at pulling out those particles. And then this is just to show that you could have a beta ratio of 100, you could have a beta ratio of 200. It only makes a difference when you do the efficiency of 99% to 99.5%. And when you look at that 0.5%, you're thinking, well, that's probably not that big a deal. But when you run it across here and you see that 200,000 particles challenge both those filters, the number of particles passing through this filter is 2,000. This one's 1,000. And that's only a 0.5% more efficient. Okay? So efficiency is key when you're looking at your filters. I think this is the last slide, and then we'll be done with this section. Proactive prevention is key. Like the STLE says, keep the dirt out, keep the water out. A lot of your problems never happen. Simply prevent entry of contaminants and moisture. Treat failure root causes, not symptoms. If you've got a problem, and let's say you run an ISO particle count and it gets real high, and you say, hey, I'm just going to change that fluid out. Okay, you change the fluid out, but have you solved the problem? You know, what's causing that? So there's people that do that. Hey, we'll just change the fluid out and not worry about it, but you want to try to find out what's that root cause, especially in what's been going on in the last year. And I think Jeff and Brad would agree with me on this, and Bill. When it's been hard for end users to get product, you know, when there's been allocations, why not take that lubricant rather than just change it out? Find that problem. Do everything you can to extend the life of that oil. Okay? Let's not throw away good oil. So that's why we're going to do condition monitoring. That's why we're going to do oil analysis. We're going to talk about that here shortly. Equip reservoirs, gearboxes, tanks with breathers, desiccant breathers. Include both filtration and drying media. Use other contamination control tools such as mechanical seals, proper sampling techniques, filtration, and appropriate lubricant storage dispensing systems. And we're going to talk about those in just a minute. So this is our break point now. We're right on pace. We're going to take another 15-minute break, come back at 11, and we're going to talk about some best practices for storage and handling.